Hi, today we are going to present our assignment for digital signal processing titled Finite Impulse Response FIR Filter Design and Application. So now I will introduce our group members. The first one is Sharvin. Next is Nurin Nadia. Next is Intan Nur Shahira. Last but not least is Runiza Eliana.
Good evening, everyone. My name is Sharvin. I'll be presenting the abstract part and the introduction part of this presentation. Signal processing filters get rid of parts of the signals that are not what you want. Filters are different from other ways of handling signals because they can block a signal completely or partially. This will usually mean that it gets rid of frequencies or frequency bands. But filters also have uses outside of the frequency domain as well. Let's take in the world of image processing, for example. There are many more things that can be filtered. Filters are mostly used in radio, television, sound recording, radar control systems, etc. What is an FIR filter? One of the two main types of digital filters used in DSP application is called finite impulse response, which is FIR in short. The other filter is called infinite impulse response. In short, it's IIR. So filters are pieces of equipment that change the way a signal acts. The goal of each filter is to let through AC components while blocking DC components through when there's signal processing going on. The best example of a filter is the phone line, which also works as one because it limits the range of frequencies to something much smaller than what human can hear. That's all from me. Thank you.
Thank you, Sharvin, for the introduction of FIR filter. So my name is Nurin Nada. We continue for the theory part. FIR filter is one that has a limited duration because it impulse response or reaction to any finite length input settles to zero in a finite period. FIR filters also may be discrete time or continuous time, digital or analog. Almost every form of digital frequency response may be implemented with a FIR filter. So to generate the filter output, these filters are often built using a multiply, adders, and a sequence of delays. The following figures shows the illustrations of FIR filter in software and hardware. So as you can see, the following equation describes the operation by define the output sequence yn in terms of the input sequence Sn. So first, the equation b0 plus b1z. This is the coefficient of the FIR filter. Next, the equation where show Sn is the input signal, Yn is the output signal, and then N is the filter order. That's all from me. Thank you.
Assalamualaikum and hi. So now I will explain for the simulation part, which is the FIR filter designed for the original part. So this is the design that we have done in Simulink. As you can see from this design, we use two input, which is sine wave, to generate impulse, and then we use 3 delay because as you can see n is 4, so the quantity of delay is n minus 1, so it will be 3. And then the output of multiplier will be applied to the input of adder, and the filter output will be taken from the adder output, which is the output will be in graph from the spectrum analyzer and scope graph. So now I will show you the simulation that we have done in Simulink. So this is the design that we have done that I have explained before, so I will run it. Okay, so this is the output for spectrum analyzer 1, and this is the output for spectrum analyzer 2. Okay, so we'll be back to the slide. Okay, so this is the result for the spectrum analyzer, which for FIR filter, the original part. So this is the graph before filter, and this is the graph for after filter for spectrum analyzer. Next is the result for scope for FIR filter. This is the graph for scope before the filter, and then this is the graph for after filter of scope. So that's all from me. Thank you.
Okay, so for now, I will continue for the implementation of FIR filter design. Okay, so as we can see, this type of FIR filter is used to implement any types of digital frequency response. So this filter was designed with a series of delays, adders, and multipliers in order to produce the output of the filter. Okay, so this figure 2.2.1 shows a second order FIR filter, which is the output is dependent on the first two input samples. And the input source, we can see that there are sine waves which are to generate an impulse. And then this filter consists of 3 stages. Since filter order is n, then the number of stages in this filter design will be n plus 1. And to sum up all the output of the filter, we use sum block at the end of the stage. And then the number of delay block used are 2, since we use a second order FIR filter. And then the number of blocks function is to serve as the xn minus 1 and then xn minus 2 delayed samples. And then we move on to the MATLAB. So this is the filter that I built in the MATLAB. So we run this. So as we can see here, this is the output for spectrum analyzer before filter, and this is the output for spectrum analyzer after filter. And then we observe the scope. For scope, when this is before filter, we get the output like this. After filter, we will get the scope like this. So that's all from me. Thank you.
In conclusion, the implementation of finite impulse response FIR filters in MATLAB and the application of it in pulse response have been studied. So the finite impulse response models are based on limited impulse response FIR filters, which are form of signal processing filter having a certain lifetime because the impulse response settles to zero in a finite period. The impulse response is referred to as finite since there is no feedback loop in this kind of filter. If the previously mentioned impulse is used, zeros will finally be generated once the one value sample has gone through all of the delay lines filter coefficient. So, an FIR filter simply takes average of the n most recent input samples and outputs the result. The coefficients which determine the actual output for a particular sequence of input samples. That's all from us. Thank you.